So today we're going to do integration by substitution. And the idea is basically that an awful lot of problems we can do by undoing the chain rule, but sometimes they get ugly, right? We did something like that on a couple of the worksheets. Every now and then you're like, oh, that's a lot of thinking to get to where you want to go. Integration by substitution is a way of making it look nicer. Doesn't make it easier per se, but it does make it easier to see, oh, that's what's going on here. Okay? The idea comes from the chain rule. Remember that if I have, for example, the derivative with respect to x of sine of 3x minus 5, that's cosine of 3x minus 5 times 3, right? So if I took the antiderivative of 3 times cosine of 3x minus 5, I would get sine of 3x minus 5 plus a constant. And again, the question comes up all the time at the beginning. People are like, where'd the 3 go? Well, the way I say it, and it's kind of weird, but you'll forgive me, the 3 is born from taking the derivative of the inside part when you do the chain rule. So when you undo the chain rule, I won't go so far as to say it's unborn, but it's eliminated. That sounds bad too. We no longer have it. Okay. So, in general, if g is differentiable and capital F is an antiderivative of f, then if we have the integral of f of g of x times the derivative of g prime of x, so we have a composite function, and we have the derivative of the inside part outside, then we can just take the antiderivative of the outside part, leaving the inside part alone. This is undoing the chain rule. Now, what we can also do is instead of undoing the chain rule, we can replace g of x with a single letter. And then du is g prime of x dx, and you get something that's nicer to look at. I mean, I think you'd all agree that this is nicer to look at than that, right? It just whittles it down to its essential characteristics. So, let me show you how this works. Let's say we have this antiderivative defined. It's the integral of x squared plus 1 to the 5th times 2x dx. So we're going to let u be equal to the inner part of the composite function. When you do integration by substitution, you'll always have a composite function, even though you may have to squint real hard to make it one. You always let u be equal to the inside part of the composite function. You don't have to call it g of x. Okay? It's x squared plus 1, and then g prime, this is du. Right? That's the derivative of u. It's just 2x. So what I have, and I probably should have written this before I wrote that out, is the integral of u to the 5th du. Right? When I replace this with u, and this is du, right? So now I just have the integral of u to the 5th. It's a lot easier to look at than this is. What's the antiderivative of 1/5 u to the 5th? Excuse me, of u to the 5th, excuse me. What's the antiderivative of u to the 5th du?
5u to the 4th.
Try again. The antiderivative
Oh, antiderivative. So 1/6 u to the 6th.
is 1/6 u to the 6th plus c. Then if we replace the u with what we said it was equal to begin with, we get this. We're replacing the u with x squared plus 1. So we're putting it back into terms of the variable that we started with. We started with an expression in terms of x. We want to end with an expression in terms of x. It's just a way of making this look a little nicer. Okay, we're going to do a whole bunch. We'll probably add some because I think we need to do more than is actually there. So let's take a look at this one. I'm going to show you on almost all of these two different ways to do it. You can do it by a U substitution, or you can do it simply by undoing the chain rule. I personally, when I don't have to use U substitution, I don't, because it's more writing, right? I'm like most mathematicians. If there's a way to go straight to it, I'll do that rather than take the long way around. All right, let me show you how to do this with U substitution. You always let U be equal to the inside part of the composite function. So here, U is going to be x squared plus 1. Then du will be the derivative of that, which is 2x dx. You can think of that as writing du dx as 2x, then multiplying both sides by dx like we do on separable differential equations. Notice that's exactly what I have. So I've got the integral of sine of, instead of x squared plus 1, we're going to write sine of u. And instead of 2x dx, we're going to write du. That is now simpler to look at than the initial one was. What's the antiderivative of sine? Negative cosine. So this is negative cosine of u plus a constant. And then we always have to replace the u with what it was equal to in terms of x. So this is negative cosine of x squared plus 1 plus c. On a problem like this, I wouldn't do it that way. I would have just gone, oh, well, I can simply undo the chain rule. This is sine of x squared plus 1 times 2x, which is exactly the derivative of the inside part. Anytime I have a composite function times the derivative of the inside part, to take the antiderivative, I just take the antiderivative of the outside part and leave the inside part the heck alone. So it'd be minus cosine of x squared plus 1 plus c. I didn't have to write nearly so much. So again, if you have a composite function times the derivative of the inside part, to undo the chain rule, you simply take the antiderivative of the outside part and leave the inside part alone. All right, for this next one, the very first thing I would do would be to rewrite it so that it's easier to see that we have a composite function and it's a power. Sine of x plus 6 to the 1/2 power times cosine of x dx. You can do that as a u substitution problem. This would be u is equal to sine of x plus 6. So du would be cosine of x dx. So my integral now, the sine of x plus 6, I replace with u. So I've got u to the 1/2 times cosine of x dx is du. So we'll take the antiderivative, that's 2/3 of u to the 3/2 plus a constant. And then some people call it unsubstituting, some call it back substituting. Doesn't matter. We'll replace the u with sine of x plus 6. Sehr gut. Okay, so here again, do I need to do all that? No. This is set up perfectly to undo the chain rule. The derivative of sine of x plus 6 is cosine of x, so I just undo the chain rule. That'll be 2/3 of sine of x plus 6 to the 3/2 plus a constant. If you can undo the chain rule, it's always faster. Now, sometimes it's not quite the way you would want it to be. Everybody got this? Okay. So again, the first thing I always do is rewrite it. And I don't know if your brain works the same way, but I want it to, if I'm undoing the chain rule, I want it to look like the result of a chain rule, which is that composite part times the derivative of the inside part, right? So I always rewrite it so the composite part is first. So secant squared of x cubed minus 7 times x squared dx. So if I'm doing this by u substitution, I'll let u be equal to x cubed minus 7, so that du is equal to 3x squared dx. Yes, ma'am. I use the inside part always as u. So it's secant squared of x cubed minus 7. It's always the inner function that I'm letting be equal to u. Yes?
Right, so even though it's not written as 3x squared, it's only x squared.
Wait, what?
So in the problem, it's only x squared.
Right, we're going to deal with that in just a second.
Okay, so when you replace du
We're going to deal with that in just a second. Hold on for just a moment. Was that the same thing you were asking about, Ben? Okay, so looking ahead, I go, I don't have a 3x squared dx. I just have an x squared dx. So what I'm going to do is divide both sides by 3 so that I get 1/3 du is x squared dx. Different people do this different ways, but I have always done it this way, and I'm like, anything else I think is too complicated. So now I'll have the integral of secant squared of u times, it's 1/3 du, but I'll factor the 1/3 out so that it's not cluttering up my integrand. What's the antiderivative of secant squared of u? Yep. So this will be 1/3 tangent of u plus the constant. So that's 1/3 of the tangent of x cubed minus 7 plus a constant. If I want to do this by undoing the chain rule, and I've talked to several of you about this at different times, I really want this to be 3x squared, so it's the derivative of what's inside, right? So I'll be like, okay, I'll make it a 3x squared, but I've multiplied by 3 so that I haven't changed the value. I must also multiply by 1/3. When I undo the chain rule, I simply take the antiderivative of the outside part, leaving the inside part alone. Now, at this point, you may be going, is there a reason for ever using U substitution? There are some, and I'll do one in just a second. It's actually not on your page, but I'll do one in just a second where U substitution is required. There's just no way around it. Okay? But most of the ones on the AP exam, actually, it used to be that all of them on the AP exam could be done without U substitution. You could do them all by undoing the chain rule. That has changed over the last several years. So that's no longer true. I used to go, why bother teaching U substitution? If you can learn to undo the chain rule, you don't need it. That's not always the case. All right, so again, first thing here, I'm going to rewrite this. I've got 2x minus 1 to the 1/3 power dx. I have a composite function. That makes me think, well, probably going to use something like a U substitution. If I let U be equal to the inner part of the composite function, 2x minus 1, then du is equal to 2 dx. Since I don't have a 2 dx, I'll multiply by 1/2. So 1/2 du is equal to dx. So now we'll have the integral of u to the 1/3 times 1/2 du. Taking the antiderivative and keeping the 1/2, this would be 3/4 of u to the 4/3 plus a constant. Which gives me 3/8 of 2x minus 1 to the 4/3 power plus a constant. Again, we could absolutely do this without doing the U substitution. If you think about undoing the chain rule, what is missing that we would really like to have right here? A 2. I'll go, okay. And then compensate for that with the 1/2. So then I have 1/2 of 2x minus 1. Oops, hang on a second. Forgot to do the fraction part. Taking the antiderivative of the 1/3 power, that'll be to the 4/3 power times 3/4, which is exactly what we got by doing the U substitution. Okay? All right. This one is, I don't know, sort of doubly composite because it's a function inside a function inside another function. So, again, I'll rewrite it. I'm going to rewrite this as sine of 5x raised to the 3rd power. That helps me to see the composite more easily. Times cosine of 5x dx. So if I'm doing a U substitution, I'll let U be equal to sine of 5x. Then du would be cosine of 5x times 5 dx. Well, I don't have that 5, so I'm going to, okay, 1/5 du is cosine of 5x dx, which is what I do have. So now we have the integral of u cubed times 1/5 du. And again, I think you can see that that's a lot easier to look at than the original is. That's the big advantage to doing u substitution, is you get something that's not so, there's too many things for me to look at. So this would be 1/5 times 1/4 of u to the 4th plus a constant. So that's going to be 1/20th of sine of 5x raised to the 4th plus c. Now, you could do it without that, but it's a little harder on this one because you have a function inside a function inside a function, and it's easy to mess it up. But if you have this, the derivative of sine of 5x isn't cosine of 5x. It's 5 cosine of 5x because of the chain rule. Doing the u substitution makes you less likely to mess that up, but maybe not a whole lot. So I'll put a 5 there and a 1/5 here. So then I'll take the antiderivative of the outside part. So it's 1/4, leave the inside part alone, of sine of 5x to the 4th plus c, which is exactly what we get.
Teachers, pardon the interruption. This announcement is for our boys soccer high school that we will be training outdoors on the practice field today. So please report to the practice field. Thank you.
Nothing quite like training on a really wet field. I remember my son playing, and someone kicked a ball and it hit a particularly wet spot, and the ball just died because it was like, he hit a puddle and it just stopped. Like, okay. Then there were like 8 6-year-olds running towards the ball at full tilt, screaming at the top of their lungs. It's like a scene from Braveheart or something. All right, so are there times when you have to use u substitution? And the answer is yes, there are. Let me show you an example that I hope works, because I just made it up in my head. We'll find out. It may not. So let's say that we've got the integral of x times the square root of x minus 2 dx. And at first you're like, okay, well, that's not so bad. That'll be the integral of x minus 2 to the 1/2 power times x dx. So I'm going to let u be equal to x minus 2, so that du is just dx. So that if I substitute, I've got the integral of u to the 1/2, and suddenly you're like, uh-oh, I have a problem here. I have this x stuck in the middle here that's not accounted for by either of these, is it? And you're like, uh-oh, can I do this? And the answer is yep. This is going to work out. What I'm going to do is I need to replace this with an expression in terms of u. So I'll just solve this for x. U plus 2 is equal to x. So the x gets replaced by u plus 2. And the dx gets replaced by the du. Now, that integrand is not nice, but it is something where I can just distribute the u to the 1/2, and then I can do the antiderivative term by term. Whereas here I have this product that I can't do anything with. So this would be the integral u to the 1/2 times u is u to the 3/2 plus 2 times u to the 1/2 is, well, 2u to the 1/2 du. Now we have two individual terms, and we can take the antiderivative of each individually. So this would be 2/5 u to the 5/2 plus 2 times 2/3 u to the 3/2 plus c. So replacing the u with x minus 2, we've got 2/5 x minus 2 to the 5/2 plus 4/3 of x minus 2 to the 3/2 plus c. Please note that it is certainly possible that in the answers in your book or on a multiple choice question that they will factor this. We can factor out an x minus 2 to the 3/2 out of both of those and a 2. So it'd be 2 times x minus 2 to the 3/2 power times, I'll have a 1/5. And if I factor an x minus 2 to the 3/2 out of an x minus 2 to the 5/2, what am I left with? X minus 2. Plus, here I'm just left with 2/3. And then typically they'll go ahead and distribute and collect up the like terms. So this would be times 1/5 x. So you have negative 2/5 plus 2/3. Wow, that's really, really messy. Negative 2/5 plus 2/3 is 4/15. So that's what's called a U sub required problem, because you can't undo the chain rule on it, because you have this x here that is neither part of the interior of the composite function, nor is it part of the dx. Okay? All right. So as you're doing the homework again, it's up to you, unless the problem specifically states to do it by U substitution. Feel free to undo the chain rule if you can see it. If you can't, do the U substitution. It makes it nicer.